Greetings, this is Paul Bamberg with the preview video for the first class of MathS322, Real Analysis for Calculus Teachers, and I'm hoping that all the students in the class will watch this before we meet for the first time on January 10th. The idea of these preview videos is to give you an overview of what we're going to be doing the next day. The material included is the first 2 pages of the handout, the so-called executive summary. And when my colleague Kate Penner and I put this course together, we set up an ironclad rule that the executive summary always has to fit on 2 pages. It'll look a little bit like PowerPoint when I start using it, only it's PowerPoint with beautifully typeset mathematics. How did I do that? Well, I used the LaTeX mathematical typesetting system, which I will encourage you to learn as part of the course, and a package called Beamer that lets you insert phrases and pauses to get the same effect as PowerPoint. The nice thing about this is all I had to do was to paste the executive summary into a new file. Why is this little lecture going to be short? Answer: no proofs, no examples. That's what we're going to be doing in class. So let's start out with our first example of a number system, the natural numbers. Kids learn about this before they start school, 1, 2, 3, and so on. And in fact, I think most children figure out the following properties of the real numbers, known as the piano axioms, and I believe these were not stated until the 20th century. They are sufficient to prove any other property of the natural numbers or counting numbers, and most of them are pretty obvious. For example, 1 is in the set of natural numbers. 2, if a number n is in the set of natural numbers, so is n plus 1. So if 14 is in the set, so is 15. 1 is not the successor of any element of the natural numbers, which means that 0 is not included. And now come 2 that are less obvious. I think this is why mathematics had to wait until comparatively recently to formulate these. If 2 numbers have the same successor, then they must be the same number. And here's what this rules out. If I didn't have this, I could count like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 10, 11, 12, 13, 14, going on forever. So this rules out the possibility that in any way the numbers loop back on themselves. And then the 5th one. This one is really subtle. If you have a subset of the natural numbers, that subset includes 1, and it includes n plus 1 whenever it includes n, then it must be all the natural numbers. You can't prove this. You have to state it as an axiom, and here's why we need it. We're going to be doing lots of proofs by induction. For example, we might have a formula for the sum of the first n integers. It's n times n plus 1 over 2. So this is really an infinite set of propositions. The sum of the first integer only, the sum of the first 2, the sum of the first 3, and we want to prove that this formula works for all integers. And as I hope you know, and as I hope you teach your students, the way you do this is you show that the case 1, so-called base case, is true, and then you prove the inductive step, which states that if the formula is true for n, it's also true for n plus 1. Now it turns out there's another much less well-known alternative to mathematical induction known as the least number principle. What the least number principle states is that any non-empty subset of the natural numbers has a least element. That is, I tell someone, write down a few integers on a piece of paper, There has to be at least one. And when I look at this, I can find the smallest one. And it turns out that this statement, along with the assumption that, as axiom 3 stated, any natural number except 1 has a predecessor, you can use those two facts to replace N5. It's only by looking at examples that you can appreciate how this works, but I'll explain to you now in general what the application is. An alternative to doing a proof by induction is you can say, I'm going to assume, for a contradiction, that there's some set of values for which this formula is not in fact correct, for which it's false. Okay, given that, we take the set of cases for which it's false. We're assuming that it's true for 1, so there must be some number k greater than 1, which is the smallest case for which this is false. If I can then prove that k minus 1 also leads to a false version, I've got a contradiction. I assumed that k was the smallest value for which it was false, and I proved that k minus 1 is an even smaller value for which it's false. Since it's got a contradiction, the only possibility is the set of cases for which it's false is the empty set. You'll see this in action in class for some standard inductive proofs. Another set of familiar numbers are the rational numbers, written with a fancy Q. It will impress your friends greatly once you can write down these fancy n's, q's, and r's. And the rational numbers can be regarded simply as fractions in lowest terms. You can't identify a rational number with a fraction because 1/2 and 2/4, though arguably different fractions, represent the same natural number. And a natural number like m over n satisfies a first-degree polynomial equation, nx minus m equals 0. A generalization of this is a number that satisfies a polynomial of any degree. Something like x to the 5th plus x minus 1 equals 0 is called an algebraic number. It's fun and frequently useful and frequently instructive to invent proofs that a certain algebraic number is irrational. To prove, for example, that the square root of 2 is an irrational number. It turns out that these proofs require a fair bit of cleverness to invent, and that it's in fact easier to do them as corollaries of a single theorem called the rational zeros theorem, which is known by every student of high school algebra, but I think is rarely proved in high school algebra courses. Here's what it says. You got a set of integer coefficients, C0, C1, up through Cn, and when you set a polynomial equation with those coefficients equal to 0, you get a rational 0. R equals C over D. I'm using Ross's notation, which is a bit unsatisfactory because C is used twice. I believe in the proof of this I changed C and D to P and Q. C over D is in lowest terms, so C and D have no common factors, and furthermore, as everyone knows, D is different from 0. And what the theorem says is if you look at this equation and C sub n and C sub 0 are both different from 0, then the numerator divides the constant C0, and the denominator D divides the coefficient of the highest term. Students of elementary algebra learn this first in the case where they're factoring quadratics, where the coefficient on the x squared term is 1, and they know that if there is any integer solution to that quadratic equation, that has to divide the constant term. We'll prove this in class and do some applications of it. The rational numbers are a well-known example of what mathematicians call a field. So are the real numbers. This use of field is quite different from the use of field in physics, say, where one talks about electric fields or gravitational fields. A field is just a set of numbers that satisfy the well-known rules of arithmetic and algebra, which I will enumerate for you. First, addition is commutative and associative. Second, the field includes 0, known as an additive identity. And furthermore, every number has an additive inverse. The equation a plus x equals 0 also has a solution, which we write as minus a. Multiplication is commutative, it's associative, and it's distributive with respect to addition. Finally, there's a multiplicative identity, the number known as 1, and as long as x is different from 0, you can always solve the equation a times x equals 1 and get another number in the field, known as the multiplicative inverse, A inverse. What you may not know is that there exist finite fields, where there are only a finite set of numbers in the field, yet all these axioms are satisfied. But in this course, we're going to deal almost exclusively with the real numbers and its subset, the rational numbers. Note that the rational numbers form a field even though the integers do not, because of the last axiom. The integer 2 does not have a multiplicative inverse that is an integer. Its multiplicative inverse is 1/2. On the other hand, every rational number except 0 has an inverse. You just interchange numerator and denominator. The rational numbers and real numbers are also ordered fields. This means you can talk about an ordering operator like less than or equal to, and this ordering operator has a number of well-known properties. For example, if A is less than B and B is less than C, then A must be less than C. And it turns out that for many properties of sequences of real numbers, the only thing we'll need to know is that the real numbers are ordered. Now we turn to the triangle inequality, a key step in most of the proofs you're going to be learning in the first couple of days of the class. Let's think of either the rational numbers or the real numbers as lying on a number line. In that case, the distance between the 2 points on the number line is the absolute value of the difference a minus b. Now, why are we going to call this the triangle inequality when we're talking just about a number line and can't even draw a triangle? Well, the name comes from the two-dimensional case. If you take 3 points in a plane, A, B, and C, and view them as the vertices of a triangle, as everyone knows, the length of any side of the triangle must be less than or equal to the sum of the lengths of the other two sides. The distance from A to B is less than or equal to the distance that you'd have to travel to get from A to B by way of C. The one-dimensional version of this simply says that the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. But everyone calls this the triangle inequality, and so will we. Now for the really important property of the real numbers, the so-called completeness axiom. On the list of field axioms are many rules of arithmetic and algebra that everyone knows. For example, the rule that minus a times minus b is equal to ab, or the rule that anything multiplied by 0 is equal to 0. These are not on the list of axioms because they can be proved as theorems, and we'll have a bit of fun proving such theorems. These theorems work for any field. They work for the rational numbers, and they even work for finite fields. However, There are properties of the real numbers that I can't prove just from the field axioms because they rely on an axiom that's peculiar to the real numbers, the statement that the real numbers are complete. And here's what I mean by that. The completeness axiom states that if you take any non-empty subset of the real numbers, we're excluding only the empty set, and we insist that that set be bounded above, for example, that all the numbers in the set are less than 7, this has a least upper bound, which is also a real number. We call it the supremum of the set and write it as sup S, and it is not necessarily a member of the set S. Here's the standard example. The set S consists of all rational numbers whose square is less than 2. The least upper bound of that set is the square root of 2, but that's not a rational number. It's a real number that's an irrational number. So there's an example where the least upper bound exists, but it is not a rational number like all the elements of the set. If you have a set of real numbers, then the least upper bound is always in the set itself. From that, we can prove a couple of remarkable properties of the real numbers. The first is called the Archimedean property, and the most picturesque way of stating it is that given an arbitrarily large bathtub filled with water and an arbitrarily small spoon, you can still empty the bathtub in a finite number of spoonfuls. Or more formally, if you have two positive real numbers a and b, there's some integer so large that na is greater than b. This is a corollary of the completeness axiom and an interesting proof that we will be doing in class. Closely related to this is the fact that the rational numbers are a so-called dense subset of the real numbers. Here's what this means. Take two real numbers, a and b, as close together as you like, 2 points on the number line if you like. In that case, you can always find a rational number, a fraction, that's larger than a but smaller than b. In fact, you can find an infinite number of such rational numbers, but we only need to prove there's one, and this proof, again, will rely on the completeness of the real numbers. Finally, let's think about how we introduce real numbers to kids in middle school. We introduce them as infinite decimals, though we don't really say that we're introducing the real numbers. Ross puts in starred sections all the things involving infinite decimals, and there's just not enough time in this course to go into them in detail. But let me point out the obvious way in which you can think of infinite decimals as real numbers. An example of a number that goes beyond being irrational, it's not even algebraic, is pi. It's a so-called transcendental number, but it's a real number. The usual way of writing pi is say it's 3.141592 ... and I can get as many decimal places as you want if you insist. So, if I consider the set of truncated decimal approximations to pi, the set consisting of 3, 3.1, 3.14, and so on, then I can say the real number pi is the least upper bound of that set. It's the smallest real number that is larger than any truncated decimal expansion. So with that comment, I'm done with this video. I'm going to upload it to YouTube and get the warning that it's a bit longer than 15 minutes, so it won't fail, but I have a proper account, so it will succeed. And I hope you've enjoyed this and are looking forward to going into the details of this topic in class on Monday the 10th.